when we talk about functions, one of their characteristics is whether they are even or odd or neither. Okay? Now, let's talk quickly about the definitions of what it means to be an even function or an odd function. First, we have the function is even if and only if f at x is equal to f at negative x. And what we're saying by that is saying that when we have an input and the opposite of the input, it still creates equal outputs. Then we have that for odd functions, a function is odd if and only if f at negative x is equal to the opposite of f at x. What we're saying by this is if we take the opposite of an input, it gives us the opposite of the output. Okay, so we can compute f at negative x and the opposite of f at x and make these comparisons. Okay, so I'm going to try and turn this into an organizer so that you can move through these problems algebraically in a well-scaffolded, well-logical way. Okay, so if we notice here, we see that we only are comparing 3 things. It seems like there's 4 here. Okay, but if you notice, f at the opposite of x, or f at negative x, appears in even functions and odd functions, so it's involved in both. So I'm going to just draw an organizer here and try and see if this makes sense. Okay? Here we have f at x, which will be given. Okay? And then from the given definition here, we're also going to compare that with f of negative x. And this is going to be computed. Okay, we actually have to do this computation. When these guys are equal, the functions are even. Okay? But if not, we move on to the next layer of comparison, which, again, if you notice here, like I said, I'm going to use f at negative x in both of them. So I'm going to compare f at negative x with the opposite of f at x. And the opposite of f at x is computed. It's not something we're given. We have to do a computation for it. And when these 2 things are equal, the functions are odd. Now, if you don't get that these 2 are equal, and you don't get that these 2 are equal, then the answer is neither. Okay? So let's just get involved in doing some examples of this, and we'll see how it turns out. So determine if the following functions are even, odd, or neither. And the function is f at x equals x squared plus 4. Okay? So let me just redraw this organizer here, where we look at the given, and we look at f at negative x, and the opposite of f at x, which I might not even have to do if I find out that the first 2 columns are equal here. Okay, so we said that f at negative x has got to be computed, and it's computed by taking negative x and plugging it in for x squared. Now that might throw you guys, plugging it in for x in f of x. Now that might throw you guys off a little bit because it says f at negative x and you would expect to be given some type of function here. But if this said f at 7, you'd take the 7 and plug it in for x. If it said 11, you'd take the 11 and plug it in for x. Okay? But the fact that it says negative x, well, let's take negative x and plug it in for x. So by doing that, we get what? We get negative x to the second plus 4. When we square a negative, it becomes positive. Gives me x squared plus 4. So we notice here that x squared plus 4 and x squared plus 4 are equal. So what we're saying is f at x equals f at negative x. So we said when these two are equal, the answer is that it's an even function. Now, this right column is not even necessary because I've already shown that the function is even. It cannot be both. So once you've shown it's even, to try to show it's odd would be futile, would be an exercise in futility, because it cannot be both. Moving on to another example. Here we're given h at x equals 2x to the fourth plus x. Well, let me set up my organizer again, where I'm given h at x. I'll compute h at negative x, and I'll also compute the opposite of h of x. Don't let the function notations fool you that they, in the definitions, they say f. They work for whatever letter h of x, negative x, excuse me, h of x, g of x. It doesn't matter. Okay? So don't let that throw you off. So like we said, we're going to compute h at negative x by taking negative x and plugging it in for x in the given function. So that is going to give us 2 times negative x to the fourth plus negative x. I'll simplify that with starting with my exponent first and then do my multiply after that. So I'll pull down my 2. And then I'm going to get negative x to the fourth. Well, a negative to an even exponent is just a positive, so I just get x to the fourth. Plus negative x is minus x. So we see when we compare h of x to h at negative x that they are in fact not equal. So here I write not equal, so it's not even. Okay, let's move over and see if it's odd. So this is our first look at doing a computation of the opposite of h of x. Well, that's fairly simple. We just take the opposite of the entire function, gets plugged in here, so to speak. So we're going to take 2x to the fourth plus x. And we'll do the opposite of that, so just distribute the negative. That appears that way on every problem. When you do the opposite of a function, you're just taking the opposite of all its terms. So that's going to give us negative 2x to the fourth minus x. And we see when we compare these two functions that they are in fact not equal. So we've got that these two columns aren't equal, so it's not odd. So this is an example of a function that is neither even or odd. Again, if the first two columns are equal, it would be an even function. If the second two columns are equal, it would be an odd function. You just have to realize that in the first column is the given, the second column is h of negative x, and the third column is negative h of x. So it's a little memorization there for how this organizer sets up, and you're going to be golden. So one more example here. Determine if the following functions are even, odd, or neither. We have g of x equals x to the fifth plus x to the third. So I'm going to, again, draw my organizer where I'm given g of x. I'll compute g of negative x, and then I'll compute the opposite of g of x. Okay? So to compute g of negative x, again, I'm just plugging in negative x for the x. Feels a little weird when you're swapping something with an x for something with an x, but it's in fact substituting in negative x, so it's a little different. So we've got what here? Negative x to the fifth plus negative x to the third. And that gives us a simplification of negative x to the fifth. Well, any negative to an odd exponent will continue to be negative, plus any negative to an odd exponent will continue to be negative. And then I'll simplify that double sign by going negative x minus, the opposite of x to the fifth minus x to the third we can see that that is not equal to the original function. So I'll make a little note here, not equal, so it's not even, okay? And then to do the opposite of g of x, which we have here, we will do what? Well, we're going to take the opposite of this entire function. So that's going to be x to the fifth plus x to the third. And again, doing the opposite of functions is just changing the signs of all the terms. So we're going to get negative x to, excuse me, the opposite of x to the fifth minus x to the third. And when we compare the middle column to the third column, we say that they are equal. So this and this are equal. So it is, in fact, an odd function. Okay? So it's all in this organizer. What these will mean in the fact that they're even or odd extends into graphs about the nature of their symmetries. That's not what's being looked at here. You're just being able to algebraically demonstrate through using these principles whether a function given to you in equation form is even or odd.